Welcome to this lecture in the PHAY0032 series of pre-formulation. Today we're going to talk about salts and salt selection. So, as ever, if you have a cup of tea, sit back and relax and start watching the video. If you don't have a cup of tea, I suggest you go and get one. I've got mine here. Once you've got one, come back and let's begin. On the screen in front of you are the learning outcomes that I want you to be able to demonstrate by the time you finish this lecture. And I need to say right at the start that this is actually a double lecture. So I'm going to release one of the videos this week and the second video will be released next week. So don't think that you've got to understand all of these things by the time this video is finished. The first thing I need you to be able to do is to define a salt. That should be relatively simple. And then we need to talk through the chemistry of salt formation. So if someone asks you, how do I make a salt? You should be able to write down the chemical equations that define how a salt is made. Now you've probably done that before, most likely when you were doing chemistry at school actually, so it's not too difficult. But we need to review that basic salt chemistry because we need that to understand how salts behave in the body. Then we're going to look at the rationale for salt selection. It's quite clear that many drugs are formulated as salts and there must be a good reason why. And it's really important that you can discuss sensibly why a salt form has been selected for a particular drug. Now, you've been doing the coursework over the past few weeks, I hope at least, and some of you have asked me, why is the coursework based on salts when we haven't actually done salts as the lecture yet? And the answer is because this is a really big topic and there's a lot of things to understand. And so by making you look at some example drugs that are formulated as salts in your coursework, I'm hoping that by the time we do this lecture, you've got a bit more understanding of what and why salts are made for in the pharmaceutical industry. There's one key thing for choosing salts in particular, and that is to improve solubility. So I'm kind of hoping that some of the examples that you've come up with in your coursework include solubility as a reason for making the salt in the first place. We also need to understand the solubility profile of a salt. Now you might think that the solubility profile is very simple, but actually the solubility of salts is rather complex and it's completely dependent upon the pH of the medium in which the salt is dissolving. So those dissolution profiles are very complicated, but they're really important for understanding what happens to a salt as it transits through the body. There's one key thing about those dissolution profiles, and that is the concept of pH max. Now, you might not have heard of pH max, and that's okay, because I'm going to explain it later on in the lecture. But it's a key outcome from this lecture that you can sort of understand what pH max is, but also you understand why it's important in terms of salt stability, especially in the body. In the next lecture, we're going to look at the dissolution behaviour of salts. And in particular, there's another concept that you need to understand, which is called pHm, or pH microenvironment. Again, you might not have heard of that term, but don't worry, I'm going to explain it. But it's really important in trying to understand how salts dissolve in different pH media. In particular, we need to look at the stability of salts. And so the final concept of next week's lecture is to look at which excipients we might put into a formulation to stabilise our particular salt. And that stabilisation is really related to pHm and pH max. So if you understand how those concepts mix with each other, you should be all set for answering the exam question later in the term. So with that done, let's take a look at salts. If I said to you, give me an example of a salt, you might pick something like this, which is table salt. And if I said to you, what is table salt? I hope you'd say to me, it's sodium chloride. Excellent if you said that. What does it look like in terms of its chemical formula? It has atoms of sodium and atoms of chlorine. Really importantly, when the salt is formed, those are actually ionic species. So it's a sodium plus and it's a chlorine minus. And the two coming together form an electrically neutral compound. Those atoms are then positioned in a unit cell to make a crystalline structure. And in this instance, the crystal habit is cubic. So when you look at salt crystals, you can see that they are cubic. On the screen in front of you are two Nurofen products that you might buy if you go to the local pharmacy. There's Nurofen Express liquid capsules and there's Nurofen Express tablets. So my question to you is, of these two products, which one contains the highest dose of ibuprofen? Or, looking at it another way, if you were a consumer and you were going into the pharmacy to buy one of these products, which one do you think has the most drug for your money? So while you think about that, I'm just going to have a sip of coffee. Very good. In fact, that's all my coffee gone, so we're going to need a break in a minute so I can go and make another one. Have you thought about it? Good. Hopefully the answer that you're going to tell me is they contain the same amount of active, sir. And I would say that's right. They do contain the same amount of active. And yet they have different masses written on the boxes. 200 milligrams in the liquid capsules, 256 milligrams in the tablets. Why is there a difference, I hear you ask? And the answer is because the tablets contain the salt form of ibuprofen, in this case a sodium salt, and so that sodium is adding to the molecular mass of the active. So that difference in mass, 200 to 256 milligrams, is really accounting for the fact that one of those products contains a salt and the other one contains the free acid. Okay? If you look at the products that are available on the market, you will see that a vast number of them are as salts. On the screen in front of you are a range of different salts. There's clindamycin hydrochloride, miconazole nitrate, metoprolol tartrate, for instance. All of these are salts. You can always tell when an active is being marketed as a salt because it has the name of the drug plus it has the name of the salt former afterwards. So it's a really easy way of looking at a box. So if a consumer asks you, is this product a salt or not? It should be really easy to answer because you just need to look at the box and see whether there's the name of the active with or without a salt former after. So that's the easy one, telling whether it's a salt or not. Slightly harder is working out whether it's an acidic salt or a basic salt. And what I mean by that is the active itself is either going to be an acid or a base in its free form. And so when it's formed a salt, it's quite difficult to tell whether it's an acidic or a basic salt in the first place. The most obvious one is hydrochloride salts, because hydrochloric acid, most people know that hydrochloride is an acid. So because the salt former is an acid, the drug itself must have been a base. So clindamycin hydrochloride, for instance, you know that the drug is basic. For other salts, it's a little bit harder, and we're going to look at a table in a minute of common salt formers for acids and bases. And it's quite a good idea to learn those, because then when you look and see the name of a particular salt, you'll be able to determine instantly whether it's an acidic salt or a basic salt. You might say to me, why are you asking me this? Is it just basic chemistry? No pun intended. And the answer is no. When we get on to looking at the solubility profiles of salts, you will see that whether the compound is acidic or basic is absolutely critical in determining how it behaves in the body. So it's a really good idea to understand whether your drug is a basic salt or an acidic salt, because it helps you determine how you might formulate it. I've said solubility is really key, and it's a really key reason for why most salts are made. But it's not the only reason. I accept that solubility is a key reason, it's not the only reason. So if you look at the table in front of you, I've written down a number of different properties that might change when you make a salt form. On the left-hand side are what I consider to be advantageous changes in the physicochemical properties of a molecule, and on the right-hand side, disadvantageous. So if we look down the list, solubility is at the top on the advantageous side, because that is the key one. But there are some others, so increased dissolution rate is really important, especially if you've got an immediate release product. Did you notice when we looked at the Nurofen product just now, it was Nurofen Express. Express meaning it's going to get into the body faster, and one of those was a salt form, and that's the reason why, because it dissolves faster. Sometimes salts have higher melting points. That can be a good thing or a bad thing, really. It depends whether you're trying to melt your material during processing, or indeed not melt the material during processing. So it may well be the case. Think about 3D printing, for instance. It has quite a high nozzle temperature in some instances. Maybe you don't want to melt the drug. Maybe you want it to remain crystalline as it goes through the printhead, for instance, or any other manufacturing process. Lower hygroscopicity is an interesting one. So hygroscopicity means the propensity of a material to absorb water from its surroundings. I don't know whether you ever did this when you were at school, but I remember putting salts onto watch glasses and leaving them overnight. And when you come back in the morning, the material had actually dissolved and formed its own solution. So some salts can absorb so much water they can dissolve themselves. It's called deliquescence. Now, as you might imagine, sometimes the propensity to absorb water is good. It feeds into why the material might have a higher dissolution rate in water, for instance. But also, if your drug hydrolyses, that means it chemically reacts with water and degrades. I hope you can see that increased hygroscopicity, and that's not easy to say, would be a negative, because you don't really want extra water getting into your crystal structure because it will degrade the drug faster. So as a consequence, and it's not a spelling mistake, hygroscopicity appears both as an advantage and a disadvantage, depending on the chemical stability of your material to water. There are some other ones, they're not quite so important, but improved photostability, maybe if you've got a drug that degrades under light. Taste, I think taste is a common one. I pointed out table salt already, and I think if I said to you, what would you use table salt for, you'd say, I put it on my chips because it makes them taste better. So salts generally improve the taste of things, especially for bitter drugs. Remember, most drugs are really bitter. Higher bioavailability, not really a physicochemical property of the salt itself, but it's a consequence of higher solubility and faster dissolution rate. You often get more drug into the body. There is one key thing, and we're going to look at it later, but obviously for a salt to cross a membrane and get into the bloodstream, a salt itself, when it goes into water, tends to dissociate and become ionised. Obviously cell membranes are lipophilic, and therefore ionised compounds won't pass through a cell membrane. So this concept of when is your drug ionised and when is it not ionised is really important to understand, because it feeds into bioavailability. It's very easy to design a salt which in a laboratory dissolves in water really well, but when you give it to a patient, it doesn't necessarily get into the bloodstream because it won't cross cell membranes. So just keep that in mind. There are a few others, processing and synthesis or purification kind of go together really. But if you think about salts, it's quite common that to get a salt form you need to crystallise it out of a solution. But in crystallising, what goes into the actual crystals tends to be a very pure material. So making a salt and crystallising it from a solution tends to be a way of purifying the compound if it's been made with some sort of organic synthesis that's left a few things in there that you don't want. And the last one is potential for controlled release. I'm going to look at that later, but it's very dependent on whether the drug was acidic or basic, and it affects how it will dissolve in different pH media. Remember, your gut is a long tube that starts at a low pH and finishes at a reasonably neutral pH, and so control of release is often linked to how that material responds to changes in pH, which is key for salts. Looking down the negative side, I've said hygroscopicity already. Increased molecular weight. Increased molecular weight is not of itself a problem. The only thing is, if you've got a high dose in a tablet and you don't have a lot of leftover capacity to add excipients into that tablet formulation, if you then make a salt form, so ibuprofen is another good example, isn't it? You can get up to 600 milligram ibuprofen tablets. If you then make a salt form of ibuprofen, then to get the equivalent dose, the mass of ibuprofen is increasing, as I talked about already. So if you've already got a high dose tablet and you made it even more high dose because of the salt form, it means you have less space for excipients. It makes it slightly harder to formulate. Sometimes salts can have reduced chemical stability. I've said why already, but generally it's because they absorb water. You might have an increased number of polymorphs. I've put that down the disadvantages column, but it could also be an advantage. You might want that. So you choose a salt form and it might have multiple polymorphs, and that allows you to choose a better one for your formulation, which is fine. Reduced dissolution in gastric media. That's a really key concept, and you might at this point say, I don't understand what you mean by that, sir, nor do I understand why it's in this table. And that's fine, because we're going to look at it in next week's lecture. That's the concept of pH microenvironment that I said already. That is related to the one below it actually, which is the same solubility in buffers. So two different salt forms, or the salt form and the free acid or base, will have the same solubility as each other in a buffer. And again, you might not see why that is, but we're going to look at that in just a second actually, so that's fine. Corrosiveness is an interesting one. Imagine that I made a salt and it had hydrochloric acid as a salt former. Then imagine that that dissociates, maybe it gets a bit wet during processing. You've got a very strong hydrochloric acid solution knocking about. Hydrochloric acid reacts really well with stainless steel. Stainless steel is often used to make all of the processing equipment that you might use in a factory to make your pharmaceutical in the first place. So therefore you've got to be a little bit careful with the salt because it can be very reactive, especially to metals. It doesn't have to be a hydrochloride salt, by the way. So I often say to students, look around you on the street outside, and do you see many cars that were made in the 1970s and 1980s? And the answer is, and I accept that you probably weren't born in the 1970s or 1980s, no. Why? The reason is because in winter, in this country at least, we put salt. It's the same salt as we looked at already. We put salt on the roads to lower the freezing point of water so that we don't get icy roads, but that creates very salty water that the cars are driving through, and so that water splashes up underneath the car. If that salt water comes into contact with metal, then it will just rust, because salt is a catalyst for rusting. So most cars in the 1970s and 80s weren't very well rust protected, and so they have basically rusted out of existence. That should tell you that something even as simple as sodium chloride is very corrosive. And the same is true when you're using salts in a factory. There's only a few others. Disproportionation simply means it might ionise, but that can be a good thing. An additional manufacturing step. So if you are going to make a salt, but you're also synthesising your active from scratch, then the synthesis is a step of its own right, and then you've got to add one additional step where you react it with either an acid or base to make the salt. So you're just adding to your cost and complexity. And sometimes salts can actually be more toxic. Partly that's because they get into the bloodstream at higher concentration, for instance. But it is quite important to recognise it's not a simple case of saying, well, I've done a study with this particular drug and it hasn't got quite the solubility or dissolution rate that I want, so I'll make a salt form and just change from the free acid or base to a salt form. You can't do that. You have to notify the regulatory authorities that you've changed to a salt form, and they consider a salt form to be a new chemical entity. So you can't change salt forms halfway through your development process. You have to start all over again. That has some consequences that we're going to come back to later. Now, I mentioned the coursework already because you should have done most of the coursework by now, and so in your head you should have at least one example of a drug which is formulated as a salt. Hopefully you've been able to discuss why it is formulated as a salt. So a few years ago there were some really good bits of coursework handed in by some students, and a very common example, and you might be nervous now if you've chosen this example for your coursework, is diclofenac. So many students have written about diclofenac over the years, and in fact I use this as an example because it first came to my attention because a student used diclofenac as an example in their coursework. So diclofenac is available as 3 different salt forms. Each one is used for a different route of delivery, and the reason is because the physicochemical properties of the salt forms change and they lend themselves to favouring particular routes of delivery. So on the screen is diclofenac potassium, which is used as an immediate release, fast dispersing formulation in gastric media, and that's why it says rapid 25, because it's dispersing very quickly when you swallow it. Diclofenac sodium, on the other hand, so not a massive change. Sodium to potassium is quite common. It's quite common for drugs to be available as both sodium and potassium salts. Is actually used in delayed release, enterically coated tablets. Okay, so in those instances, the tablets have got a film coat which stops them dissolving in the stomach, and they will be releasing in the GI tract later on at a higher pH. And diclofenac sodium is better at that pH. And the last one is diethylamine, so diclofenac diethylamine, which is actually used for transdermal. So if you've got a bit of an ache and a pain, maybe a bit of muscle soreness, and you want a bit more local pain relief, then you often use a gel. It can be an ibuprofen gel or a diclofenac gel. So you rub that in, and it should slowly go across the skin and ease the pain. So diethylamine is much better for going across the skin than the potassium or the sodium salt. So that's just an example of one drug, 3 different salts, 3 different routes of delivery, or at least 2 routes of delivery, but delayed release or immediate release. So I said we need to look at basic salt chemistry, and we're not actually going to go through the chemistry of salt formation until we've had a coffee break. But when I did chemistry at school, there's one thing that the chemistry teacher said to me, which I've never forgotten. Partly I've never forgotten it because he said to me, when you go to bed at night, hit your head against a pillow and say the following: acid plus base gives salt plus water. Okay? It's really important that if you try that yourself, make sure you don't have anything hard underneath the pillow, like the edge of the bed or something, because you could knock yourself out. So just make sure you've got a really soft pillow, maybe a teddy bear or something like that, and just try that. Acid plus base gives salt plus water. I was 15 when I was at school and the teacher taught me this, and I haven't forgotten it, and it's well over 30 years later. I know I don't look that old, but I am, trust me. 30 years, never forgotten it. So your basic reaction for forming salts is acid plus base gives salt plus water. On the screen are 2 classic examples. HA is an acid, the H being a proton which the acid can donate, and it's reacting with a strong base, in this case sodium hydroxide, which is a classic strong base, and it will give you A minus, Na plus, which is your ionic salt, plus water. The bottom example, I've just removed the water to make it slightly easier. So it's a base plus hydrochloric acid gives you BH plus, which is your ionic salt, Cl minus to keep everything neutral. We're going to come back to the chemistry of salt formation in just a minute. Salt forms are very common. When I last looked, more than 50% of all marketed drugs are salts. And so it's really key to understand why that is. And nobody makes a salt for no good reason. So I've given you some example reasons in the table we just looked at. But it's really important to try and understand, why has this drug been made a salt? It's not always for solubility. There are a couple of references down here. The top one is a paper by Sirajuddin. Now, if you've done any literature researching for your coursework, and I hope that you have, you probably come across papers by Sirajuddin, because he's done a lot of work trying to understand pharmaceutical salts. And it's one of those things where you read papers in the literature and you associate one particular person with a whole series of really good papers, and they become a bit like a guru to you in your head, even though you've never met them. And so I was in a conference in America a few years ago in New York, and Sirajuddin himself happens to work at a university in New York, and it was the one that I was visiting. So I actually got to meet him. And I can tell you that he was a really, really nice guy. And it's one of those amazing things in science, when someone that you've read so many papers of, you kind of hope they're a really nice person. And when I met him, he was a really nice person. So I highly recommend reading all of the papers, not all, most of the papers that he's published on salts, because there are some really good examples. So there's one on the screen, it's a review paper. So if you get the chance, have a look at it. Now, before we take a break, I just want to look at salt formation itself, some of the key properties that we need in order to get good salt formation. In principle, any acid and base can react with each other to make a salt, okay? But I'm sure you remember, any chemical reaction is essentially a position of equilibrium. It's very tempting to think, oh, what we do is we add the drug, let's say it's a basic drug, and we add it to hydrochloric acid. Instantly, it all reacts and we get 100% salt form. You won't get 100% salt form because it's a position of equilibrium. You're going to get 90, 95%, but you won't get 100%. But if it's in the 90s, it's okay, because it will crystallise out, you can filter it, but you're still losing somewhere up to 10% of your drug if you've got a 90% conversion rate in the final synthesis step. So imagine that. You're a pharmaceutical company, you've just spent loads of money investing in this chemical synthesis to make your active. The last step is turning it to a salt form. Yes, it's 95% converted to the salt. You've just thrown 5% of your active away, haven't you? Because that's the nature of chemistry. So it's really important to select your salt former to drive the formation of the salt as far as you can. And one way of making sure that you kind of achieve that without actually doing the experiment is to look at the pKa values of your salts former and your drug. Now, again, I'm rather old, and so when I was taught chemistry, when we looked at acids, we looked at pKa, and when we looked at bases, we looked at pKb, okay? pKa and pKb are really easy concepts, because if you have a molecule and someone says it's got a pKa of 7, you know it's an acid. If they say it's got a pKb of 6.5, you know it's a base. It makes life so much easier. But for some reason that I don't fully understand, at least in the pharmaceutical world, every drug is given a pKa, and so it's really not possible to know, looking at the fact it's got a pKa, whether the drug's acidic or basic. It's possible to know it's one or the other, because it has to be an acid or base to have a pKa. But you can't say whether it's an acid or base just from that value. It's really confusing, and I don't understand why pharmaceutical people do it. But the bottom line is they do it, and so we have to stick with it. So just don't take that to mean every drug you're looking at is an acid. Look at the chemical structure of the drug and decide, is this an acid or a base? Looking at its formula, not looking at the fact it's got a pKa. What you can do, however, is if you know that you've got a particular molecule with a particular pKa and you want to choose a salt former, you want that salt former to have quite a different pKa. And so really you want a strong acid or base salt former. And so acid and base strengths are defined in the pharmacopoeia. So I've just picked some. They're essentially the same between the European pharmacopoeia and the US pharmacopoeia. There's a slight difference, but essentially it's the same classification. It doesn't really make a difference as far as we're concerned. So the table in front of you shows you acid and base strength based on pKa value. So for an acid, if the pKa value is less than 0, it would be deemed to be a very strong acid, the sort of thing that's going to dissolve your arm off in seconds if you put it in there, which I don't recommend, by the way. If it's between 0 and 4.5, then it's deemed to be a strong acid. It doesn't really matter what the properties of your drug are. It's not going to be a strong acid or a base. It's going to be a sort of weak or very weak acid or base. Doesn't matter exactly what the pKa value is right now. So if you use a very strong or a strong acid or base salt former, the chances are you will get very good completion rates in your salt forming reaction, because the difference in pKa between the salt former and your drug is likely to be quite high. Okay. The same is true for bases. If the base has a pKa greater than 14, it's deemed to be very strong. If it's between 9.5 and 14, it's deemed to be strong. Same argument applies. You can therefore choose a strong or very strong base, and you should get a good reaction with your drug, no matter what its pKa is, because it's going to form somewhere in the weak to very weak category. You would not actually, before we look at the next slide, use a weak or extremely weak acid or base to try and form a reaction to make a salt, because none of it will actually proceed to make a salt, and your position of equilibrium will be towards your starting material, not your salt end. So in principle, any acid or base can form a salt, but generally you need that difference in pKa to be at least 3. It's a rule of thumb, and so it's not an absolute value, it's just as a guide. If you make sure that your salt former has at least a 3 pKa difference from your drug, then you should be guaranteed that you get a decent amount of salt formed when you react them together. This is called the reactivity potential, so it's really key. If someone says to you, why have you chosen this particular salt former, you can say, because the pKa difference between it and the drug is greater than 3, and that should mean I get good salt formation when I do it. Before I look at that, because I've created a couple of graphs to show you for that, there's one other thing to note, which is that if the pKa of the base is really low, the salt itself is unlikely to be stable at physiological pH. It's kind of unusual to have a drug, basic drug, with a really low pKa, but it may happen. But the reason it's likely to be unstable at physiological pH is because in the body, the maximum pH is going to be around 6.8, and it will drop down to around 1.5, depending on where you are in the GI tract. But it's never going to go above that. Okay. And when we look at salt formation later on, you'll see that has the consequence of driving the salt back to the free base. And so although you can make it, by the time you've given it to someone, it's dissolved in their body somewhere, it will convert back to the free base. So it's really important that if you've got a pKa really low for your drug, it's probably not worth formulating as salt, even though you can, because in the body it won't stay as a salt. And if you look in the literature, you'll see that actually no marketed salt exists that's got a pKa of less than 4.5. for that reason. So you do need your drug to have a pKa value up in the 6s, 7s, 8s and so on in order to use salts. And the last point on this slide, and I mentioned it already, it's really important if you're going to use a salt that you make that decision early. Okay? Toxicity, as well as all manner of other physicochemical properties, change if you make a salt form. And that doesn't mean all salts have the same physicochemical properties. Different salts also have different physicochemical properties. So you have to notify the regulatory authority which one you're going to develop, because they consider each one to be a different chemical entity. So if you've done a whole load of development, maybe you've even wandered into clinical trials with, let's say, the free acid or base, and you think, oh, that's not working very well, so I'll change to a salt. It's too late. You've got to start the whole process again. You could waste a huge amount of money, and you really don't want to do that. Why do we need this difference in pKa? What is it about this pKa difference on a chemical basis that means these types of materials will then react together? The answer is that it ensures both species are going to be ionized in solution. So remember, think about the salt, even the sodium chloride that we talked about already. Sodium plus, chloride minus, they come together, and it's the ionic interaction which is really important. If you don't have that ionic interaction, then you won't form the salt in the first place. So clearly, in order to get these materials to react in solution, they need to be ionic, and then they can come together and neutralise. So that's the key one. The next thing on the slide is really obvious, but I'm going to say it anyway, which is that the pKa of the acid that you're using to form the salt must be less than that of the weak base, and the pKa of the base must be higher than that of the weak acid. If you don't do that, it's very unlikely, because you would have had to select a really, really weak acid or base salt former. But if you did do that, no reaction will occur. You'll get no formation of salt at all, and your equilibrium will lie right with the starting products, and so that would not be good. Now, many years ago, when I was writing the textbook that you might have flicked through that accompanies this lecture series, I needed some graphs to try and fill the pages of that book, and so I thought, well, that's interesting. I wonder if it's possible to calculate what percentage of reactions should occur as a function of the pKa difference between the acid or base and the salt former. And the answer is, it is possible to calculate that with the Henderson-Hasselbalch equation. So we're not going to look at that exactly, because you don't need to know how to calculate this in order to answer the exam question. But you do need to kind of understand what percentage of salt should form as a consequence of this pKa difference. And also, it's a good idea just to have it in your mind a little bit, because it will help you see how much material you're wasting if you don't choose the salt former correctly. So I calculated this graph from the Henderson-Hasselbalch equation. It's on the screen now. Looks like a simple curve, doesn't it? But I can tell you it is generated on a mathematical basis. On the y-axis, it shows you the percentage of salt that will form if you react your drug and your salt former together. And on the x-axis is the pKa of the salt-forming acid in this case. So this graph is showing you if you have a basic drug with a pKa of 7.5, which is a very reasonable middle-of-the-road pKa for a drug substance, and you select a particular salt-forming acid, it shows you how much salt you can expect to form because of the difference in pKa. Now, let me talk you through the graph. It's much easier if we go through each example. So on the x-axis, I hope you can see that at 5.5 on the x-axis, there is a dotted line going up. So if the pKa of the drug is 7.5, and the pKa of your salt-forming acid is 5.5, the difference in pKa between those two is 2. So it says delta pKa, difference in pKa, is 2. If you go up and you hit the line, the black line, and then you go across and you read the value on the y-axis, that tells you the percentage of salt that should be formed if you react those two together under ideal conditions. And so I hope you can see 91%, a theoretical maximum of 91% salt if you react your basic drug in this case with an acid with a pKa difference of 2. So if that was a really expensive drug that you spent a long time synthesizing, and your final step is to do this salt formation, and your pKa difference is 2, you are throwing away 9% at best of your drug. because the theoretical maximum yield is 91%. In practice, it will probably be slightly lower, but in theory, at least, it should be 91%. If you move down the x-axis and you go to 4.5, you can see there's another line. Again, pKa of the drug is 7.5. If the pKa of your salt-forming acid is 4.5, the difference is 3. So it says delta pKa 3. Follow that line up until you hit the solid line. Go across, you can see you're just short of 97%. So roughly 3% of drug you're losing because it's not forming the salt. So 97% is pretty good. So your basic rule of thumb always, pKa difference of 3 should get you at least 97% conversion to a salt when you react them together. You can go further. 3.5 is obviously a difference of 4, so that's delta pKa is 4, and now you're at 99%. And I want to draw your attention to the fact that you'll never get that graph to 100%. There'll always be some fraction which is remaining unreacted because it's a position of equilibrium. Okay, so 99% is around about as good as you can do. If you think about it, if your drug has a pKa of maybe 7, 7.5, and you're using hydrochloric acid or sodium hydroxide, either of those is fine, depending on whether it's an acid or basic drug, then you have a pKa difference of 6 at least. And so you're going to be well past 99%. So you should get quite a decent conversion when you do the reaction. This table in front of you shows you the frequency of marketed salts. And what I mean by that is we have a choice of either anion or cation for our particular drug substance, which is the most common used on the market. And so if you look at the table, you'll see that the top line in each of the sides, the anion column and the cation, is empty. And the reason for that is because I'm going to take a sip of coffee and I'm going to let you think for a moment. What do you think the most commonly used anion is, and what is the most commonly used cation? So I'll give you a second just to think about it. Now, admittedly, I didn't give you very long, but hopefully the answers should have popped into your mind because we've seen them already. So the most common anion would be hydrochloride, and we're going to look at some reasons for that after the coffee break. And the most common cation is sodium. I hope you said that too. In fact, nearly 63% of drugs on the market, acidic drugs at least, are sodium salts. So there's a number of reasons for that, and again we're going to come back to that after the tea break, but hopefully that doesn't come as a surprise to you. But you can go down that list and you might see some of those names you might be very familiar with. Citrate forms, for instance, quite common. Succinate, mesylate, they're quite common names. Maybe on the cation side, principally because sodium is the most commonly used cation and potassium is the next one, and then calcium. Between the three of them, they've basically cornered the market in cations, so you might not have seen a lot of the other ones, and you've got to be a little bit careful. So the aluminium salts, you don't really want aluminium building up in the body. Zinc and magnesium maybe, but they're very common, less commonly used. So you normally need a really good reason to use one of those cations. So it's usually sodium, potassium or calcium, and you might recognise that those are three elements that are very common in the body. Right, last thing to say, and then we'll stop for a cup of tea, is that you do need to think a little bit carefully about valency. Valency means how many electrons has your counter ion lost or gained, depending on whether it's acid or base. And so I've just given two examples on the slide. One is diclofenac sodium, which we looked at already. So sodium has a valency of 1, and therefore when it reacts with an acid, in this case, then there's only one acid molecule can react per sodium. So diclofenac sodium has only one drug molecule in it. But the other example is atorvastatin calcium. So calcium has a valency of 2, so it's calcium 2+. So what that means is when it reacts with an acid, acid is CO2H in this case, so one of the electrons from the O- can interact with the calcium. That's fine, but that's 1, and calcium's got a valency of 2. And so the only way it can become neutral is if 2 molecules of drug bind to 1 calcium, because that makes the whole thing electrically neutral. So in this instance, atorvastatin is available as a calcium salt, but it's a much bigger molecule because now it's a dimer. So it's just one to think about. Obviously, it doesn't make much difference in terms of the dose of drug in the tablet a little bit like the ibuprofen we looked at earlier. It actually has less effect, you see, because it's one counter ion for 2 molecules of drug rather than 1 for 1, which is what we had for ibuprofen. But it's just about in your mind recognising that by using a counter ion with a valency of 2, then you have made a dimer, and that may have a consequence in the body. So with that, we're going to stop, go make another cup of tea, have a break, walk around for a bit, and when you're ready, come back and I'll see you for part 2.